Alright, so chapter 16 is over Earth's atmosphere. Here are your vocab words. You have atmosphere. Again, this is the second time we've seen it. Water vapor, which I think we know what that is. The troposphere, the stratosphere, the ozone layer that we've talked about, and the ionosphere. We're going to talk about all of these in a little bit. So I'll let you guys record these, and I'm going to move on. So the importance of the atmosphere. The atmosphere extends hundreds of kilometers above the surface of the Earth. So it's not just what we think of as where weather happens or where the top of the clouds are. It's much, much, much bigger than that. You can think of it as the atmosphere of the Earth is like the skin on an apple. So that's how small it is. It's small compared to the rest of the Earth, but it's still, when we think of things, hundreds of kilometers is very big, but small compared to the Earth. The atmosphere contains oxygen, water, and carbon dioxide. We need at least two of those things to live, and without the third thing, so we need oxygen and water to live. And without the third thing, plants wouldn't be able to live, so no more oxygen. So if you really think about it, we need all three of those things to survive. It moderates the Earth's temperature. Without the atmosphere, the Earth would just be scorched by the sun. It keeps us in a regular zone so that we can kind of predict the temperature. It also provides protection, not only from UV rays, we've talked about the ozone layer protecting us from UV rays, but meteors as well, kind of a doomsday idea there. We have a lot of meteors burned up in the atmosphere. The origin of the atmosphere. The Earth started as a molten ball of rock. As it cooled, volcanoes released hot gases, which created the atmosphere. The ancient atmosphere was mostly water vapor with a little bit of carbon dioxide and nitrogen. As the Earth cooled, water vapor condensed into water. So we have that gaseous water, so water that's in the air, that condensed down into water. However, there wasn't enough oxygen to support life in the early atmosphere. This is why the first organisms carried out photosynthesis, for the most part. Consuming the carbon dioxide and releasing oxygen played a large part in shaping today's atmosphere. So those first organisms consumed carbon dioxide from the atmosphere and started producing oxygen. And that's when we were able to start evolving. So the composition of the atmosphere, we've talked about this before, 78% nitrogen, 21% oxygen. All our gases are trace amounts. There might be 1% of the extra stuff being argon, but regardless, it's still a very small amount compared to nitrogen and oxygen. There's solids in the atmosphere and liquids. Solids can include dust, pollen, ash. Ash from volcanoes would be the main one that we would think of when we talk about ash. We also have liquids, microscopic water droplets. Those are things that form clouds. That's that water vapor that we were just talking about. We've seen this before. This is the breakdown of the amount of each gas. So obviously nitrogen is taking up a large chunk, oxygen with the smallest. Then here we have our little slivers of argon, carbon dioxide, and all other gases. Layers of the atmosphere. The troposphere extends from the Earth's surface upwards to between 8 and 15 kilometers. The temperature decreases as altitude increases, and we'll see a picture of this at the end of how the temperature zigzags back and forth depending on what layer of the atmosphere you're in. So for the troposphere, we have temperature decreasing as the altitude increases. The stratosphere extends from the end of the troposphere, so 15 kilometers, to 50 kilometers, I should say, above the surface. The lower portion contains the ozone layer, so at the bottom, so about 15 kilometers above the Earth's surface is where the ozone layer is located. As altitude increases in the stratosphere, temperature increases. So this first one, when we think of going higher, if you've ever been in the mountains, it gets a little bit colder the higher you go up. So it starts off and it gets cold. After you exit the troposphere, it starts to get warm the higher that you go. Next layer we have is the mesosphere. This extends from the bottom or from the top of the stratosphere, which is 50 kilometers, to about 85 kilometers above the surface. The temperature decreases as altitude increases. So this is going back to getting colder as you go higher up. Next we have the thermosphere, which goes from 85 kilometers, so the end of the mesosphere, to 500 kilometers in altitude above the Earth's surface. and here we're going to zig back. So we've gone from as altitude increases, temperature decreases, and then it increases, and then it decreases again in the mesosphere, and now it's going to increase one last time. In these two spheres, the mesosphere and the thermosphere, 1% of all gas is located. That's a small amount. That's a teeny tiny amount, and we're going to talk about why there's not very much gas in those areas. These layers are also the layers where most meteors burn up. So when we talk about burning up, they start to hit more molecules, and that increases the friction, and that friction causes heat, which is what causes them to burn up. So the ionosphere is from 60 kilometers to 50 kilometers in altitude. It's part of the mesosphere and thermosphere. It has a bunch of different interesting properties. It can reflect AM radio waves, so we use this to bounce radio waves around the globe. It's where auroras take place. If you ever heard of aurora borealis or the northern lights, that's what happens. That happens in the ionosphere. This occurs when the ions from the sun strike the air molecules, and those air molecules emit a very vivid light. The aurora borealis or aurora, I'm not sure what the southern one's called. Best seen at high latitudes, so near the North or South Pole. Our last layer of the atmosphere is called the exosphere. If you've ever heard of exoskeleton, that exo prefix means outside. Gas pressure and density are so low in this layer that molecules hardly ever collide. However, after the gas molecules absorb the sun's radiation, they move extremely fast. So you heat something up, it's going to move a lot quicker. And that's what we see here. There is no defined edge of the atmosphere, or, in this case, the exosphere, because that's our last layer. Some particles will escape the pull of gravity, and those just end up in space. So there's nothing in space, it's just very, very sparsely populated. So here we have a picture of our different layers. Again, we have troposphere, stratosphere, ionosphere, which is made up of those two other layers, the mesosphere and the thermosphere. And then our last one is the exosphere. As you can see, the troposphere is where the top of the clouds go. So if you've ever seen pictures of clouds topping off, or it looks like they're flat on the top, it's because they don't go into the stratosphere. What we're looking at here is the type of lights that can go into each layer. Visible light, obviously we can see that. Infrared and radio waves can make it in. Otherwise, everything else, ultraviolet, X-ray, gamma, and cosmic rays, all get burnt up before they reach us. Here we have a picture of the auroras. This would be right here, obviously, the light that's being emitted. I've never seen it. I'd really like to. I think it's really cool. Alright, so air pressure and altitude. This is going to be the slide that's going to take quite a bit of thinking. Got to put a few things together here. So air pressure is caused by gravity pulling on molecules. So when you think pressure, you think something being pushed on. In this case, you can think of it being pulled on. And what it is it's that gravity that wants to attract everything together is pulling on individual molecules, and that's what we feel as air pressure. The pressure that a column of air exerts on anything below it is called air pressure. So air pressure is caused by the pulling of gravity on molecules. The pull of gravity on air also increases the density of air. So when we talk about density, we're talking about the number of molecules in a certain space. Like when we talked about population density, we were talking about the number of animals in a certain area. Now we're talking about the number of molecules in a certain area. So here are some of the relationships that you might need to know. As density increases, air pressure increases. So as density decreases, air pressure decreases. This is saying that if you have fewer things in one area, then you're going to have less things pushing on an area. And that makes sense, right? There's nothing, hopefully that is pretty straightforward. So as altitude, and when we talk about altitude, we're talking about the distance above Earth. As altitude increases, air pressure decreases. The way I remember this is mountains. As you go up into the mountains, the air pressure decreases, and that's why your ears pop, because now they're starting to expand out a little bit more. Your eardrums are. So as altitude increases, air pressure decreases. Therefore, as altitude decreases, air pressure increases. These things go both ways. All right, now our last one. As altitude increases, so as we go higher, density decreases. So as we go higher, there's going to be less molecules around. And we saw that when we were talking about the exosphere. The higher we got up, the exosphere said there's almost no particles in there. There's almost no molecules of gas up there. So this is what we're talking about. Here we have altitude on our y-axis and atmospheric pressure on our x-axis. And this graph is kind of inverted because we're starting, say we start at sea level, and this would be the average pressure is 760 millimeters of mercury is what that's called. We're not going to get too caught up with that. But we have 760 millimeters of mercury, and you can see as we start to go up, we start to go over. Right? So as altitude increases on the y-axis, we have a decrease on the x-axis, a decrease on the pressure. So here you can track it all the way up. So pressure starts getting lower and lower and lower. And Mount Everest is about 8 kilometers above sea level and has 250 millimeters of mercury as the pressure compared to 760 at sea level. Here we see the picture on the left is altitude on the y-axis and then temperature on the x-axis. So starting with lower temperature here and moving to higher temperature here. So like we talked about, as you increase altitude in the troposphere, you start to decrease temperature, right? You start to get colder. In the stratosphere, it's the opposite. You go back and you start to increase. Mesosphere, you start getting colder again. Thermosphere, you start warming up again. So there's this zigzag that happens. Here on our right side, we have a column of air, is what we're looking at. So these blue dots represent individual air molecules. Don't worry about these numbers, I'm not worried about that. But what I want you to understand is that because gravity is pulling downward, and we're saying that this is at sea level, you can see that the density here, or the number of molecules in this area, is much greater than the number of molecules at the top of the column. So, this column down here exerts air pressure because we have air molecules pushing down on a surface. Alright, that will do it for our first slideshow for this chapter.